Hello there. This is a quick video that will hopefully help you with the idea of kind of the introduction to both reflections and rotations when we're talking about symmetry. So this is just a brief overview about what they are before we get in depth with them. So I'm going to actually start with reflections. All right, so reflections, I just have a couple pictures here. If you notice, reflections, they're you think of symmetry, a lot of times you think of reflections, the reflection symmetry, where this would be a line and it divides a picture, or in this case, it's a butterfly directly in half. So it reflects itself onto itself, kind of like you think of a mirror. There's a reflection. It's the same picture, just backwards. Um, Also, if you look into water, you see the same idea. So we're going to talk about properties of symmetry, specifically reflection properties. So first of all, reflection symmetry. The word reflection symmetry simply means when a figure has reflection symmetry, if you can draw a line that divides the figure into halves, should be halves instead of have, that are mirror images. So you have a picture there. You can draw a line. It divides this thing. This line divides the thing in half. So if you folded it over, it would go right on top of itself. And that line is actually called the line of symmetry. So that is the line of symmetry is the line that divides the figure into halves that mirror images. Now something that's a little bit um, different from when you think of symmetry, just cutting something directly in half so that it's exactly the same on both sides. What we're going to talk about a lot in this chapter is when you have a figure and it's completely mirrored, the whole figure, not just half of it cut in half. A whole figure is mirrored. And in this case, where's the line of symmetry? It's right between the two. So if it was perfectly between the two, those two would fold over at that exact spot, and then go right on top of each other. That is what the reflection symmetry that a lot of the reflection symmetry that we will be talking about in this unit. Now, I had you do this with a partner, but a couple examples, just looking at a picture and figuring out how many lines of symmetry, because some things do have multiple lines of symmetry. So figure out how many there are and where they are. So for instance, this first example, I know if you cut it right in half like this, and you'd have to have a perfect line, but if you cut it right in half there, that would fold over onto itself perfectly. Now you might say, well, this is a rectangle. What if you cut it like this, the horizontal way? Now you could, the rectangle would be that way, but none of the designs on here would actually be symmetrical, because if you folded over that long horizontal line, it would not be the same exact on both sides. So that one is not a line of symmetry. In this case, there's only one line of symmetry. This one below it, though, you might have more than one. I think if you do the long way, it should work. Yep, that would be the same on both sides. You could also do it vertically, as long as it's right down the middle. If it's off to the side a little bit, it would not be exactly symmetrical. So this one has two. See, the only thing that's tricky here, it looks like you could have diagonals, but in fact you couldn't. Let's take a look. Let's say if you tried a diagonal, um, it would fold over onto itself, but not all the designs would match up. For instance, this design and this design would not match up onto itself. They're different colors, and they would not even land on itself, because you can see this one is a lot closer to the line of symmetry than this one. All right, so there are only two in this one as well, and that would be up and down and left to right. Let's see, F would have 0 lines of symmetry. You could try as many as you'd like, but up and down would not work. It wouldn't fold exactly onto itself. Diagonal would not work. There would be flaps hanging over. Other diagonal would not work. Horizontal would not work. There are no lines of symmetry for that one. Whereas in letter G, there's actually 3. This is an equilateral triangle, meaning all the sides are congruent. And if you do this, whoops, meaning if you would cut it like that, looks like it didn't stay. If it was perfect like that, it would cut it directly in half. You could fold it over that line and it would match up. You do the same thing right here. You can also do the same thing right here. The neat thing about these is all these lines of symmetry would actually intersect at one point, and that would be called a point of concurrency, but we'll get to that later on in your math career. So that is how you find how many lines of symmetry. Because if you look at this, I'll throw some red ones that would not work. Try cutting it in half like this. Ah. Try cutting it in half like this. That would not fold over exactly. Try cutting it in half any other way, like this. No, no, no. All those red ones are no-goes. Those would not work. But those three in the black would. Now, I want you to think outside the box and think about a couple of things for the homework. And one would be looking at letters. If you have the alphabet, so many letters in the alphabet actually are symmetrical. And I want you to find, if they're capital letters, I want you to find where they're symmetrical. So you can draw them and draw the lines of symmetry. For instance, for A, if you go up and down vertical, that would be symmetrical. B would actually be symmetrical horizontally. C would also be horizontally symmetrical. And D. And E, I guess. F, I don't think there is any symmetry. H, you could argue two of them going across like that and going like this. Same thing with I. M we could do vertically. O we could do, depending on how the O looks, you could definitely do vertically and horizontally. And you can go on with that. Same thing with shapes. We just did some shapes. Make sure that the designs look the same. For instance, this one would have, looks like, actually diagonally would work for this one. If you did diagonal, that would work for both of those. But I think up and down or left to right would not work. There's some more figures down here. The last one is consider some state names written in capital letters. Now, you have to look up some of the state names, but we want to see if there's any reflection symmetry going left to right, or if you write it up and down. And I can think of one, and maybe you can think of some more. But if you write the word oh, hi, oh, there would be a line of symmetry. This would actually work both ways. Written horizontally, there would be a line of symmetry like this. It technically would look the same if you flipped it over, if you drew it perfectly. Same thing if you went vertically. Oh, hi, oh. You could do a line of symmetry right down the middle, and it should also match up because all of those have vertical symmetry. That's kind of neat. So that is the idea of symmetry. And reflection symmetry. And now I want to talk just briefly about the other type of symmetry that I want to touch on is rotation symmetry. Now you see rotations a lot in the world. You might not think that rotations are actually a type of symmetry, but rotating wheels, the Earth rotating, technically it doesn't have symmetry because it looks different everywhere on the Earth, but the Earth rotates. Clocks, well, I guess the clocks do, the hands rotate. I don't know if you can find specific symmetry with that, but there's lots of different ways. There's symmetry, windmills, helicopter blades, things like that show rotation symmetry. So if you could draw a picture of a crayon box, we're going to talk about degrees of rotation. So it says draw the picture shown to the right, how it would look if it were rotated 90 degrees counterclockwise. So counterclockwise, you think of a clock, they go kind of turn to the right. So that means we'd have to turn this way to the left in 90 degrees. And you might not think of you know, what that means, but 90 degrees, if you think of 180 degrees, that'd be flipping completely over. So I can rotate, this would be 180 degrees. So 90 degrees would be half of that. You only rotate it to the side. That is a 90-degree rotation if you rotated the whole thing. Now the interesting part is when we get to graphing, we're going to pick one point to rotate it around. So let's say I want to rotate it around this point. I wouldn't just rotate it. I would also slide, or it would rotate like this, but it'd also come all the way over here. So it'd be kind of rotating like the hand of a clock. And that's what I like to think about. So if we talk about degrees of rotation, you have 90 degrees would be a quarter of the way around. 180 degrees would be halfway around, or just flipped backwards. 270 would be 3/4 of the way, and back around would be 360 degrees. And we're going to be talking about degrees of rotation, so you got to get the idea of this picture memorized. All right, so rotation symmetry, and I'm going to change this a little bit. Rotation symmetry, a figure can rotate, should be 360 degrees counterclockwise. So rotation symmetry means that a figure can rotate less than 360 degrees counterclockwise to look the same as the original. So if you rotate something less than 360 degrees, and however you rotate it, wherever it lands, it looks exactly the same as where it started, then it has rotation symmetry. All right. So if you look at these three pictures, technically you could argue that they all have rotation symmetry. For instance, if you look at the windmill, you could rotate the windmill. If you're just looking at the blades, you could rotate it a quarter of the way over. That would be a 90-degree rotation. You could rotate a whole another all the way up. So this windmill you're starting with, this would be a 180-degree rotation. All the way over to here then would be 270, and 360 would be back here, or 0 degrees, or 360 degrees. So that one has four rotations, four possible rotations that would make them symmetrical. This one, it looks like we have 6 different sides that would be the same. 1, 2, 3, or maybe there's 6. 1, 2, 3, 4, 5, 6. So if you rotate, you can rotate a total of 6 times to get it back to the original. So this would go 1, 2, 3, 4, 5, 6. That would bring you back to 360 degrees. All right. And the last one, looks like we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 possible rotations to get back to the original. So this 6, so this 4. Now there's 2 words that you need to know with rotations, and that's the center of rotation, which would be the fixed point about which you rotate the figure. So if you look above, the center of rotation for this windmill would be right in the middle there, where it rotates around. Same thing with the snowflake, and the same thing with the wheel. And you think of a wheel, you think of the axis, and that's where the center of rotation would be. So that's the first term. Angle of rotation. If you're talking about the angle of rotation, you're talking about the smallest possible angle through which you can turn the figure in a counterclockwise direction so that it looks the same. So in this case, our angle of rotation was, we could do it 90 degrees and it look exactly the same. That's the smallest rotation. This one, I guess 360 degrees total, and you can do 6 rotations. So it would be 60 degrees. Again, this is the angle of rotation. This one was 12, so if I do 360 total degrees divided by 12, you would get 30-degree rotation. All right, so those would be the angles of rotation. All right. So, quick little practice. Got some questions for you here. And this is looking at the pictures before. A says, list all the terms less than 360 degrees that will rotate the pinwheel. So we're talking about the pinwheel here. This is the pinwheel that we said that has 12 rotations to a position that looks the same. What is the angle of rotation on the pinwheel? Now, I laid that down here. This might help. Any multiple of 45 degrees, it says. The angle of measure of rotation would be 45 degrees. Now, I calculated 30 degrees. And now I forget why I said 45 degrees. Because if it was 45 degrees, that would mean that there's only 8 different possible rotations. And that looks like to me like there would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So, or 12. So there'd be 12. And I'm going to actually say, so we'd have 30 degrees, 60 degrees, 90 degrees. And the angle of rotation is the smallest one, so that would be 30 degrees. All right. So actually, now I lied to myself. That should be for this one. This should be, the angle of rotation should be 30 degrees for the wheel of the wagon. The pinwheel, that's another story. All right. We'll just skip down here. Let's do one more. All right. How about we do D1 here? And a copy of the hubcap. And we have a copy of the hubcap for number 1 there. Mark the center of rotation. So we're going to say the center is right about in the middle where it's rotating. Then find all the turns of less than 360 degrees that will rotate the hubcap to a position in which it looks the same. So it looks like we could rotate it 1, 2, 3, 4, 5 times. So let's do 360 divided by 5 to see what that first one is. And I believe 360 divided by 5 would be well, let's check that out. I can do the mental math, but I want to make sure I'm right. I think it's going to be 36 degrees. 360 divided by 12. Sorry, divided by 5. Yeah, it's not going to be 36 degrees. 360. It's going to be 72 divided by 5. There it is. 72 degrees. So we'd have, that would be our angle of rotation. And so we'd have 72, 144. Another rotation would get you to 216. Another rotation would get you to 288. And then you get all the way back up to 360. All right. Tell whether the hubcap has reflection symmetry or not. If it does, draw the lines of symmetry. This one to the left, which is what we're looking at, does. There's reflection symmetry. There's reflection symmetry. There's reflection symmetry. There's reflection symmetry. And there's reflection symmetry. If it were perfect, that's what it would be. So good review of reflection symmetry and rotation symmetry. And I hope this helps you dealing with both reflections and rotations, just an introduction to them. So as we move on, you will do well. All right. Have a good one. Good one.